Wait, recording. Okay. So let's continue what we go over last week and wrap up the first half of the class with out of order execution. As I told you guys, today we have a guest speaker, my daughter, with me. So she might be speaking random things. I'm sorry about that. There might also be cat sick in the background. So today's video will be really chaotic. All right. But we're gonna do recording regardless. In any case, let's go through our material. There'll be also sample exam questions that I posted on Canvas already. We'll go through the out of order execution question. And then for the rest of it, please do check it out. And next week, I'll basically spend like the first maybe 20 or 30 minutes talking about any question from the exam. We will talk about what's the logistic for the midterm. That will happen in 2 weeks at the end of this class today, right? So that we are all aware of the when it's gonna happen and what's the format. Hint, it'll be online, all right? I'm not gonna get all the way to Rayong. I was there last Thursday, actually, if you didn't saw me, basically, in Ajahn Saranat lab. And it was like a 6-hour from Bangkok to there, and then from there back to Bangkok. It's a long car ride. All right, so a quick review from lecture 4, right? We talk about issue with multi-cycle execution and also things like how do we need to make sure that we need to maintain sequential order. And again, we need to maintain sequential order because we want to make sure that from the programmer point of view, right, we still follow von Neumann model, which is sequential instruction processing. The first instruction is supposed to finish first, followed by the next instruction, and so on and so forth, right? Then we talk about precise exception. How do you handle exception when you try to have a super scalar architecture and run things out of order to some extent, right? And this precise exception basically kind of conclude with we need this because we have von Neumann ISA, right? It helps software debugging and it's make it easy to basically recover from exception and interrupts, right? And it allows like a pretty easy way to restart the process. Okay, all right, cats. And how do we ensure precise exception? We talk about then the reorder buffer that essentially the key idea is I want to store instruction that I fetch, and I'm gonna fetch a bunch of instructions at the same time, and I will store this in this thing called instruction window, right? This will allow me to run things in whatever order that I want, but at the end, before we write back, we want to make sure we reorder everything back, and to do this, we have this buffer area where you store all the instructions that were being dispatched. And we now, because we store that, we know the order, and we just retire the order's instruction in the order, in the sequence that we see from the code, right? And to do this, basically, when you dispatch, you reserve an entry in the reorder buffer, you write the result and instruction complete, and the ordered instruction in the ROB or the reorder buffer will be right back, right? And the problem with reorder buffer, as we show here, is with this code, right, you have multiple versions of R3. So let me draw this quickly. You see that this R3 is used here. Then there's another instruction that generate R3, which is used by this guy, and another instruction that generate R3. There's R3 version 1, R3 version 2, and then R3 version 3. But on your CPU, you only have one R3, right? You cannot essentially store 3 different versions of R3. So how do we fix this problem? To fix the problem, right, we can do something like register renaming. Essentially, the key idea is what you saw earlier is the right after read and right after write hazard. Sometimes you have the later writes being dispatched before the earlier writes, or the later writes that were dispatched before the earlier read. In the out of order pipeline, this is problematic because we cannot guarantee precise exception, right? And with this, right, with the reorder buffer, we are good. but it's not efficient enough. We need renaming. Renaming means that whenever I allocate a reorder buffer entry, I would assign an ID with that reorder buffer entry. And then the register, instead of the actual value, will point to the ID so that you know exactly where is my data. We go through an example from last week on how this work, right? This particular example, right? You have the add and multiply and add instruction, right? Every time you have new instruction, you just add the entry in the reorder buffer, right? And then you assign the tag, right? And the tag, oops, sorry. The tag will store, right? Just the unique ID that the register file can point back to, okay? Then we talk about the further optimization with the history buffer and the future file. So the way history buffer works is, I want to add this buffer that if something happened, I want to undo. It's essentially store a series of things that happen from the architectural state. Again, architectural state is what the programmer see. Then we can undo the updates. When exception happen, you undo using the history buffer, okay? Then the difference is with the reorder buffer, it actually more of the, I want to store the architectural state with the non-speculative value. This can delay execution. Okay. And then the history buffer, right, will update the register file aggressively. Then if something happened, you go back in time to your checkpoint in the architectural state so that you can handle exception. We can use both of them. This is through the future file. Essentially, future file add one set of register file. One of the register file, we call it architectural register file. This is the same old register that the programmer see. Whenever you finish an instruction, you update the architectural register file. It only have the old value before the write back. Then the future file is the aggressive one that go ahead in the future. Depending on whatever we're trying to do in the pipeline, we keep updating the value for the future value. We call it the future file. This is going to get updated as soon as the instruction complete either from the ALU or the memory. And this is used speculatively. When I say speculatively, basically means that I try to predict what's going to happen in the future, right? And then update the future file accordingly. And then we use the architecture file to update the state. This is used for the state recovery during exception or interrupts. All right. And we go over the example here from last week. So if you want to go over this material again, please check out the last week video because otherwise you'll spend too much time on this, right? Then you have to overhead. Actually, a few more overhead. First of all, you need to maintain 2 copies of the register file, right? This can be costly. Basically adding another copy of the register file. So the solution is, well, can we do some kind of indirection and only have one single storage to store the register data and create the mapping for future and architectural value? The structure is called the register aliasing table. You're going to see it in the example today. So I'll go through this example today. All right. But before that, kind of let me kind of wrap up the out of order execution before we go through the full-blown example in the second half of this class. This future map is going to be speculative based on the register value, and the architecture register file is used for state recovery. Wow. Okay. So you can use the future file with the register table. So the way it works is you have each ALU will have its own register aliasing table. When you dispatch the instruction, right, you put that in the register aliasing table. that will have the ID that corresponds to the instruction. Again, I'm sorry about this. I'm not going to go through this particular example because we have a better example on the practice exam, which we will go over next. All right. And then the last thing we talk about is we need checkpointing. Checkpointing, basically, think of it as a load and save point when you play games, right? Whenever you have branches, you need to make a choice. Are you taking the if? Are you taking the else? Are you branching or not branching? And sometimes the speculative state, because you do out of order execution, right? You're basically doing an instruction that you're not supposed to do. So what you need to do if you mispredict is go back to the original if else, then execute the different path. All right. Basically go back to the original if else and execute the different path. Uh, and then the checkpoint copies are updated with the instruction to produce a register file. All right, sorry, that's the wrong way. You're trying to poke my ears. Okay. And upon branch misprediction, you restore the checkpoint future file and you flush the instruction in the pipeline. Right? This allows you to remove checkpoints that come after the branch. And basically keep going with the correct execution. Okay. And with the correct execution, then if you see another branch again, do you then checkpoint again, right? And depending on the branch outcome, you basically cannot go back to the checkpoint that you stored earlier. All right. So that's a recap of what we go over last week. Okay. Today we'll put everything together and talk about out of order execution and how it works, right? All right. So again, this is basically dynamic instruction scheduling. You think about it, right? The scalable, I mean, not the super scalar architecture allow you to dispatch instruction in whatever order they are ready. If I have future instruction that I can execute now, I'll just execute them. There's no need to wait. Okay. But from the assumption so far, like let's say you're a software programmer, you doesn't really care what happened in the hardware, right? Because you want the abstraction of the hardware that works for you, right? The thing is, you're gonna assume that the scaling decision is done by software. In other words, it can be done in the compiler, for example, right? Or by the programmer itself, by from the way how they code the program, all right? The question is, we can also have the hardware to schedule the instruction dynamically, right? The older instruction can stall the pipeline if you don't do that. But if you have future instruction, don't poke your ears. But for some future instruction, you have nothing to do with the result. You don't need any earlier result. You can dispatch them. They're independent, right? Because these are independent instruction, you can dispatch them. They're ready. They have the data to execute, right? Again, that's the key, right? Here, this is the key of out of order instruction, out of order execution, my bad. And here's the thing, you can actually figure out how your decoder would dispatch these instructions, and it can be done in a pretty logical steps that you can follow, right? So again, the key idea is we want to be able to dispatch things out of order. If we have dependent instruction, let them wait. But if I have all the source overran, if I have both of my inputs for my instruction ready, dispatch them. The benefit is obviously this is going to be faster because you can execute future instruction, right, as needed. And I know. So the key component is, so first of all, you need this thing called reservation station. Think of it as it's a window, right? It's a window that if a certain operation can be dispatched, we will schedule them. Sometimes we call this a scheduling window, okay? And with this, right? Wait. You then need the reorder buffer, right? To make sure that you retire things in order. We still follow one Neumann. All right, you still follow one Neumann. Anything else you need? for the future file technique, right? You can use the register aliasing table or the register rename table to further enhance the performance and lower the cost. You don't need 2 copies of the register file. Okay, so here's how the reservation station work. Okay, think of it as whenever you want to fetch an instruction, you keep fetching. Basically, the fetch will keep fetching new instruction, and it will fetch into the reservation station all the time, right? Again, the key idea, I will keep fetching new instruction. Some of them will be ready. I can run right away. Some of them will not be ready because I need previous instructions data, right? Then to figure out, can I dispatch? The station will maintain the active instruction with the operation and the operand. Basically, I'll remember what do I need to dispatch, right? And then when all the operand are ready, I dispatch them. All right. So that's the key idea. Let me recap this in Thai just to make sure that everyone is on the same page, because this is basically the important next step. All right. ก็คือว่าไอตัวดีไซน์เราตอนเนี้ยเราต้องการที่แน่ๆเราต้องการ make sure ว่าตอนเรา write back อ่ะมันกลับมาที่ order เดิมก็คือ instruction 1 2 3 4 5 6 7ใช่ไหมครับแต่เราอยากสร้างฮาร์ดแวร์ที่ทำให้เราสามารถ dispatch instruction โดยที่ถ้าสมมุติมี instruction นี้90 11ที่สามารถรันได้ก็จะรันไปเลย วิธีทำก็คือไอตัวที่เราเคยเรียกว่า instruction window อะฮะเราจะใส่ ability ให้มันเราจะเรียกมันว่า reservation station ก็คือเรา fetch แบบ fetch แหลกเลย fetch มาเรื่อยๆจะเรื่อยๆจนกว่าไอตัวเนี้ย station เนี้ยมันจะเต็มถ้ามันเต็มก็คือจะหยุด fetch แต่ถ้ามันยังไม่เต็มมันก็จะ fetch ไปเรื่อยๆนะครับขึ้นมาก่อนลูกโอเคก็มันก็จะพอมัน fetch ไปเรื่อยๆฮะมันจะเก็บข้อมูลว่ามันต้องใช้ operand อะไรบ้างในการรัน instruction นี้ถ้า operand มันมีสมมุติเราสามารถไปหยิบ operand นี้มาได้เมื่อไหร่ปั๊บครบ dispatch ถ้ามันยังรอ operand ตัวไหนอยู่ก็ยังไม่ dispatch ก็ยังรอไปก่อนนะครับอันนั้นก็คือไอเดียคร่าวๆของ reservation station นะครับ All right, so the next thing is we need to deal with register renaming. How do we do it, right? ไม่ไปทำงานค่ะ register ID is then renamed to the reservation station entry that hold the register value, all right? Again, the register ID hold the reservation station entry. The artificial register ID is holding the physical register ID, okay? And the information in the register aliasing table, the RAT, will store the tag, the valid bit. Give me a second. แป๊บนึงนะครับแมวอยู่นู้นลูกแมวแป๊บนึงนะครับ All right, now we're back. The information in the RAT will contain the tag, the value, and the valid bit. The tag allows the register to search whenever it points to the tag. It knows the data, or it knows that, okay, I'm waiting for this data. The value and the valid bit will contain the data itself and whether you can use the data or not. Okay. And this eliminates the case where the same register from 2 instructions have nothing to do with each other, that impact each other. This is register renaming. Okay. And virtually enable performance of having a lot of register, even the ISA when they have only a few register. All right. So here's an example of reservation station example, right? You basically, all right, that was my cat. Sorry, so chaotic today. So you have an instruction that have the tag, right? For example, tag A, tag A, B, and C, right? Then source 1 will be either some value or a tag. In this case, be like a prime that is like an earlier instruction, right? And the destination means that I'm going to generate something for this tag, right? Then you can develop a systematic way to schedule this through the Tomasulo algorithm. So here's the idea. If the reservation station is available, before register renaming, the instruction and the register source and its tag is inserted to the reservation station. Then you perform renaming if reservation station is available. Okay. Basically, if I have the reservation station entry, put new entry in. If it's not available, I stall. Inside the reservation station, each instruction is going to watch for a common data bus for the tag. Basically, everything in my reservation station is going to wait for some data, and this common data bus will declare, if you need this tag, here's your value. So everyone watch for that. And if that's the tag that you want, you grab the value. Once the value becomes available, you update the reservation station. If both of your value are available, then you dispatch. All right. Then after the instruction finish from the functional unit, is then your job to declare that, hey, who needs this tag? Here is the data, right? So that's done through the common data bus. And the register containing the tag would indicate the latest writer to register. You can write the value into the match tag, then set the valid bit, say, hey, this value becomes valid. Then you can reclaim the tag if there's no valid copy of the tag. All right. Again, this is the second important part of this particular lecture. I'll explain this in Thai again. All right. ก็คือถ้าเราจะต้องการ dispatch ไอตัว instruction นะครับ เราก็จะใช้สิ่งที่เรียกว่า Tomasulo algorithm ในการช่วยได้ไอเดียของ Tomasulo algorithm ก็คือว่า entry ที่อยู่ใน reservation station น่ะมันก็จะบอกว่าสมมุติเราต้องการ add ใช่ไหม add มันจะใช้2 input ที่เป็นตัวซ้ายกับตัวขวาคือเอา operand ตัวซ้ายกับตัวขวาของเครื่องหมายบวกนะครับแล้วไอ้2ตัวเนี้ยถ้าเรามีค่าอยู่แล้วที่เราใช้จาก data forwarding logic หรือใช้จากค่าของการแบบสมมุติ register เนี้ยมัน available อยู่แล้วเนี่ยเราก็ใช้ค่านั้นได้เลยแล้วก็ dispatch ตุ้มเรียบร้อยนะครับพอเรา dispatch เสร็จเราก็จะ run แล้วพอเรา run เสร็จปั๊บสมมุติเราบวกเสร็จแต่ยังไม่ได้ทัน write back เนี่ยคือสมมุติเรายังไม่ได้ write back เนาะแล้วเราบวกเสร็จแล้วอ่ะเราก็จะไปอัปเดตใน reservation station ของตัวเราเองบอกว่าค่าของการ add ของเราเนี่ยจะเท่านี้นะฮะถ้าในอนาคตมีใครต้องใช้มันจะไปหยิบค่านั้นมาใช้ได้ส่วนถ้าสมมุติ input เรายังไม่พร้อมสมมุติว่าเราต้องการบวกแต่ไอตัวซ้ายยังไม่เสร็จมันเป็นแบบ R5 สมมุติเป็น R5 เนาะ R5 มีคนกำลังอัปเดตอยู่เราก็จะใส่แท็กว่าคนที่จะอัปเดต register ตัวเนี้ยคือแท็กไหนเสร็จแล้วทุก instruction ที่อยู่ใน pipeline ก็จะพยายามรันไปเรื่อยๆสมมุติเรา execute เสร็จปั๊บเราได้ค่าของ instruction เราแล้วปั๊บเนี่ยสิ่งที่เราต้องทำคือเราก็บอกว่าเราจะรู้ว่า instruction เราเนี่ยแท็กคืออะไรผลลัพธ์ของ instruction เราคือแท็กอะไรเราก็จะบอกทุกคนว่าเฮ้ยใครต้องการแท็กอันนี้นี่คือผลลัพธ์ของเราเพราะฉะนั้นถ้าใครรอผลลัพธ์อันนี้อยู่ก็จะบอกว่าโอเคเราก็จะวิ่งไปที่ common data bus แล้วก็หยิบค่านั้นออกมานะครับพอเสร็จแล้วปั๊บเนี่ยถ้าเรา instruction เราเสร็จปั๊บเราก็ broadcast attack นั่นเองมีคำถามไหมครับมีคำถามไหมเอ่ยคือมันอาจจะดูยาวแต่คอนเซ็ปต์ง่ายมากๆก็คือว่าเราก็เก็บทุกอย่างไว้ใน reservation station ตรงนี้แหละแล้วถ้าเราได้ input ที่ต้องการปั๊บ run พอเรา run เสร็จปั๊บเราก็จะบอกทุกคนว่าใครต้องการ input อันนี้เอาไปได้เลยนะครับแค่นั้นเลยคอนเซ็ปต์นะฮะ
ผมมีคำถามเล็กๆหน่อยได้ไหม
ได้ครับ
คือตัว reservation ตัวเนี้ยครับมันทำงานแบบเอกเทศหรือว่ามันต้องทำงานขึ้นกับตัว clock ด้วยครับเวลามัน
คำถามดีมากทำงานขึ้นกับทุกคอมโพเนนต์ในดิจิตอลคอมพิวเตอร์ต้องทำงานโดยการซิงก์กับคล็อกเพราะว่าลอจิกเวลาสมมติเราจะให้ลอจิกมันมีซีเควนซ์ว่าอันนี้ตามด้วยอันนี้ตามด้วยอันนี้เนี่ยแต่ละแอคชั่นมันจะต้องอยู่ใน1 clock อย่างน้อย ไม่งั้นมันจะตอบไม่ได้ว่านี่คือแอค
นี่
ชั่
คื
น
อ
เดียว
action
กันห
เดี
รื
ยว
อ
กั
ว่าน มัน
หรื
เป็
อน ว่า
แอ
มั
คน ชั่
เป็น น
สอง
action
แอค
สอ
ชั่
ง
น
แอ
ที่
ค
เรา
ชั่
ต้อน ง
ที่
แย
เรา
ก
ต้องแยกกัน
มันก็เลยจะ
มัน
ต้อ
ก็
ง
เลย
ไป
จะ
ซิ
ต้อง
งก์
ไป
กับ
ซิงก์กับ
ครับโอเคครับ
โอเคคำถามดีมากเลยจริงๆอันเนี้ย All right, so let's put everything together by going through. Well, actually, let's talk about benefit first. All right. So the benefit is we are faking the data flow model. In lecture 1, we talk about data flow versus one-Neumann, right? And we have the outcome that say, hey, one-Neumann is much easier to code. I can write ISA easily. I can write assembly easily. But whenever we do out-of-order execution, we follow data flow. Whenever I have the input ready, I fire off the operation, right? So this is basically, sometimes we call this as restricted data flow machine, right? We can build the data flow machine now, kind of faking it, basically using out-of-order execution. Some of the restricted parts are things like, first of all, right, the reservation station. These are actual buffer. It has size, right? There are limits to how many instructions can you fetch, right? So it's still restricted by your data dependency, right? For those of you, for example, ask the question, why do you need to learn functional programming? To be honest, these kind of the way to program, the functional programming kind of, it's really friendly toward like data flow model. It's kind of the same thing, right? So when you program the way that is more friendly toward data flow model, it allows like other execution to get even faster to run your code, right? Also, remember, memory is not in the picture yet. Memory will come right after we go through the example. All right. So actually, let's talk about it now or not. Let's not talk about it now. Let's actually take a quick break. We'll go through an example midterm that I post on Canvas, right? What I want you to do, because basically this is kind of almost a wrap for the earlier part of the first half of the class, right? Basically, I want you to, you can all access Canvas, right? Anyone here cannot access Canvas? Please download the sample midterm that I post on the module. It's going to be called F19 VISTEC midterm exam or something along that line. Check it out, read the question. There'll be one question that is about out-of-order execution. We'll go through that question right after the break. All right, so let me take a quick break. To be honest, I just want to check my daughter if she's okay. And then we will be back at maybe 10 o'clock, so we have more time to like process the sample exam. And also, in case you have further question about other things on the exam, you can ask during the review section of this of today. All right, so let's do a quick break. I'll be back at 10 o'clock. If you have any question, feel free to ask me. If you cannot access the sample exam, let me know, but please go check them. All right, we'll be right back.